Good afternoon. My name is Omar, and we're back at Physics News Network. Today, we'll be investigating an exciting experiment involving projectile motion. Our team conducted a lab using a projectile launcher to determine the muzzle velocity of a ball and predict how far it would travel at different launch angles. Using the laws of physics, we compared theoretical predictions with real experimental results. Let's head over to Mark while he shows us further information.
Thanks, Omar. We're here at the physics lab and we're trying to find out the muzzle velocity of our experiment. So what we were using this little trigger, this mini launcher. And if you come to this side, you could see right here, you could get the angle on the protractor of what type of launching trajectory that you want. So the idea was to get the muzzle velocity, we had to do a bunch of trials. What we did is we went from 30 to 45 to 60, as well as 0 to get that trial. We press the ball back in, we'll pull the trigger, and from right there, we'll get the angle or the measurement of the distance that it flew in that trajectory. We did that a total of 3 times for each angle, and that's what gave us our muzzle velocity. Oh. Oh, money shot. All right, fellas, here it goes. Oh! Good job.
Have you ever wondered how soldiers hundreds of years ago managed to hit targets that were far away without calculators, computers, or even modern physics? Back then, firing a cannon wasn't just about lighting a fuse and hoping for the best. It actually required careful calculations, teamwork, and a deep understanding of motion, even if they didn't fully realize the physics behind it yet. Okay, so for the real world example, I want you to imagine this. In early warfare, cannon operators had to predict where a cannonball would land. But the path of a cannonball isn't straight. It follows a curved path called a trajectory. Before physics was fully developed, this path looked complicated and unpredictable, and in fact, teams of people were often assigned to just estimate distances, angles, and timing to improve the accuracy. It wasn't until scientists began studying motion that they realized something important. This complex curved motion could actually be broken down into simpler parts. So the basics of this trajectory is that projectile motion has two independent components. The horizontal motion, which is on the x-axis, and this moves at a constant velocity. And then we also have the vertical motion, the y-axis, which is affected by gravity. Although these motions happen at the same time, they don't affect each other directly. When combined, though, they do create the curved path that we see. This discovery made it much easier to predict where an object, like a cannonball, would land. In our lab, we are basically doing the same thing those early cannoneers did, but with better tools and equations. Instead of a full-size cannon, we use a mini launcher and a steel ball. Our goal is to predict where the ball will land when launched at different angles. So, besides sending things flying, what is the real-world importance of what we learned? Well, these same principles we used in this lab are applied in many real-world situations today. Engineers use projectile motion to design systems like water fountains or safety equipment. Athletes rely on it in sports like basketball or soccer. And of course, modern military technology still depends on these calculations, just with far more advanced tools. So, in conclusion, what once required teams of people and guesswork can now be solved within a few equations and careful measurements. By breaking motions into components, we turn something complex into something predictable. And that's exactly what physics is all about, understanding the world by simplifying it.
Now that we have seen how the experiment was conducted, let's take a closer look at the data collected during the investigation. Our first goal was to determine the muzzle velocity of the launcher. To do this, we fired the projectile muzzle We fired the projectile horizontally from a height of 0.89 meters and 0 degrees and measured how far the ball traveled before hitting the ground. We performed three trials and measured horizontal distances of 1.29 meters, 1.26 meters, and 1.30 meters. When we averaged these measurements, we found the average horizontal distance to be approximately 1.28 meters. After determining the muzzle velocity, we launched the projectile at three different angles: 30 degrees, 45 degrees, and 60 degrees. For each angle, we recorded three trials and compared the experimental distances with the theoretical distances predicted by projectile motion equations. For the 30-degree launch, the projectile traveled an average distance of about 1.60 meters, while the theoretical prediction was 1.62 meters. This resulted in a percentage error of approximately 1%, which shows very strong agreement with the theoretical model. For the 45-degree launch, the experimental average distance was 1.47 meters, while the predicted distance was 1.52 meters, producing a percentage error of about 3.3%. For the 60-degree launch, the experimental distance averaged 1.15 meters compared to the theoretical distance of 1.38 meters, giving a percent error of approximately 16.4%. Reflection questions. Where do your percent errors come from? Our percent errors come from differences between the experimental measurements and the theoretical predictions. These differences are mainly caused by measurement uncertainty, small variations in launch velocity, and environmental factors such as air resistance. Question 2. Do you think there are factors affecting your experiment that are not considered in the formula we are using? Yes, the equations assume ideal conditions where only gravity affects the motions, but real experiments include other factors such as air resistance, friction in the launcher, small variations in launch speed, and measurement uncertainty. That also answers question 3. Which ones? Again, reiterating the fact that the main factors would include air resistance, measurement errors from recording distance, slight variations in launch speed, possible misalignment of launch angle. Question 4. Are they significant? These factors are usually small but can become more noticeable at certain launch angles. They can affect the final landing distance, especially when the projectile stays in the air longer. Do you think there is a way to minimize that error? Yes, error can be minimized by performing more trials, using precise measuring tools, carefully aligning the launcher angle, and ensuring the launcher releases the projectile consistently. Averaging multiple trials can also reduce random errors. Are all your percent errors equal? Why or why not? No, the percent errors are different because each launch angle changes the projectile's flight time and horizontal velocity. Higher angles can produce larger errors because the projectiles stay in the air longer and become more sensitive to measurement errors and air resistance.
In conclusion, this experiment allowed us to better understand projectile motion by breaking it into its horizontal and vertical components, and using those to predict where an object would land. By first calculating the muzzle velocity through a horizontal launch, we were able to apply that value to launches at different angles and determine theoretical landing positions. When we compared our predicted results to our experimental data, we observed some differences which were reflected in our percent error calculations. These errors likely came from factors not included in our model, such as air resistance, small inaccuracies in measuring angles or distances, and slight variations in how the launcher released the ball each time. Despite these sources of error, our results were reasonably close, showing that the equations of motion are effective for modeling projectile motion under ideal conditions. Overall, this lab demonstrated how physics can simplify complex real-world motion into manageable calculations, while also highlighting the importance of precision and the limitations of theoretical models when applied to real experiments.